Hi everyone. In today's video, we're going to talk about performing image convolutions in JAX. We will compare the convolution output from JAX with the convolution output from PyTorch. Hopefully they will produce the same thing, because at the end they are performing the same mathematical operations. So let's get started. So I got this notebook with my notes all over the place. First, I would like to acknowledge the help of this tutorial, Generalized Convolution in JAX. It was very helpful to understand how the convolution functions in JAX, and I also borrowed some code from that tutorial. So before we jump into the code, let's understand the convolution functions in JAX and PyTorch. So if we look at flax-conv, it takes the features, which is the image, the batch of images, and the kernel size, and it wraps flax conv general dilated. Flax is actually a library under JAX. So flax calls the same function from JAX, conv general dilated. And what JAX is doing, it performs convolution using this exact same function, conv general dilated. It takes left-hand side, which is the image, and right-hand side, which is the kernel. Think about these two functions just like in PyTorch. If you look into torch.nn.conv2d, you're only passing the in channels, the out channels, and the kernel side. You cannot pass a kernel that you initialized. The kernel will be initialized for you, the convolution kernel. It will be initialized using the initialization function specified in this. But if you look into torch.nn.functional.conv2d, you can pass the input and the weights. What are the weights? The weights are the kernel, the convolution kernel. So you can initialize it and pass it to this function. So these two functions, functional.conv2d and nn.conv2d, are the same as flax.linen.conv and jax.lax.conv general dilated. And I got this in my notes. So these two functions, the flax one and the torch one, you cannot pass a kernel to these functions. Kernel is initialized using the default initialization function. You can only pass the kernel size, and we usually initialize the kernel. The kernel is usually initialized randomly. But in these two functions, they give you more flexibility. You can pass your own kernel. So you can pass a kernel to these two functions, and if the dimensions do not match, an error will be thrown. One more note about convolutions in JAX. If you look into the description of this function, the conv general dilated in JAX, it actually wraps XLA's conv operator. XLA is accelerated linear algebra. It is this function. Here is a conv. It calls this module. So JAX uses XLA convolutions. So XLA convolutions has this pseudocode in explaining the 2D convolutions with padding and striding. Image convolutions, as you might know, is passing a filter across the 2D image. So we're putting a filter in one position of the image. That position is called the receptive field. And we're computing the convolution, which is dot product, and we are summing all the pixel values. Then we're moving the convolution filter to the next position. So you can think about it as a nested for loop, just like what is explained here in XLA documentation. But basically, it can be implemented efficiently using matrix multiplication. So if we take this example, an image of 32 by 32 by 3 channels, and we are passing 4 filters of size 5 by 5. So this is the filter, and this is the image, and we're passing 4 of these filters. We can flatten all the filters. Then we can flatten all the receptive fields in the image, and we can perform matrix multiplication. At the end, we will end up with a 2D matrix, giant matrix. Then we can reshape it to the convolution output. I think this is how it's implemented in XLA library, but I'm not sure. I looked into the source code, but I couldn't find a lead that it is implemented as a matrix multiplication. But this is, in the documentation, they mentioned that each 2D point is associated with 1D vector. They are flattening all the receptive fields. If they are flattening all the receptive fields, they might be doing it as matrix multiplication. So basically they are doing this. They're flattening all the filters and they're flattening all the receptive fields in the image, and they're performing matrix multiplication to get this matrix and reshape it at the end. This is the algorithm of it's usually called M to col, image to column. So here is the start of the code. I'm importing libraries. Here I'm importing torch, and here I'm importing JAX. I'm setting the random seed for torch, and I'm using this random seed for all the random initializations in JAX. And I'm setting dark background for all the plots. Then I'm importing CFAR dataset. So here are the 10 classes in CFAR dataset. And then I'm specifying the transform. The transform transforms each image into a torch tensor, and it normalizes each image between these values. Then I'm calling the test set by setting the train parameter to false, and I'm downloading the dataset, and I'm performing the transform that I specified earlier. Then I'm putting the test set into a test loader, and I'm setting the batch size to be 32, and I'm setting the shuffle to false. Then I'm pulling the first batch using next iter from that test loader. So here is the size of the first batch. It's 32 images by 3 channels and 32 pixels at the height of the image and 32 pixels at the width of the image. The data type for the first batch is torch.float32. Also comes with the first batch the labels. These are 32 labels, so one-dimensional vector with each label with label for each image in the batch, and it's of type torch.int64 because labels are always integers; they don't have decimal point. Then I'm creating 4 filters randomly using JAX.random.normal. Here I'm setting the random generator to random seed that we specified earlier, and I'm setting the shape for the n-dimensional array to be of size 4 by 3 by 5 by 5. 4 is the output channels, 4 filters. 3 is the in channels, 3 channels, RGB channels. These are color images. And 5 by 5 is the width, the height and the width of the filter. Here is the n-dimensional array I'm getting from JAX. It's of size 4 by 3 by 5 by 5, and its data type is float 32. Now let's perform convolutions using the filter that we initialized randomly on the first batch of the CFAR10 dataset. So here we are calling torch functional.conv2d, and we're passing the first batch of CFAR10 dataset. 0 here to indicate that we're passing the images. We are not interested in the labels. And we are converting the kernel that we initialized randomly into a torch tensor, and we're setting the padding to valid. What valid padding means, here is a great explanation. So padding equals valid is the same as no padding. Padding equals same, pads the input, so the output has the same shape as the input. So if we go back to this example here, our example, the input size, here we're setting, here the padding we are performing is valid padding. The input size of the image input size is 32 by 32. The output of the convolution is 28 by 28. So why is that? What's the difference? What brings us down from 32 to 28 is that there are only 28 unique locations that we can place this 5 by 5 filter in. So if you slide this 5 by 5 filter and we move it one step at a time, there are only 28 by 28 unique locations across this image where we can put the filter in. But if we set the padding to same, it will pad the image with zeros, so the input is 32 and the output is 32. So that's why that padding equals same. But here we are setting the padding to valid. Here we're printing the shape of the convolution output from PyTorch. So we got 32 images, 4 filters, and 28 height and 28 width. And the data type is torch.float32. Here we're doing convolutions in JAX. At the beginning, we are converting the first batch to be of type JAX.rumpy. Here. And we're printing the shape. So the shape is 32 images by 3 channels, 32 height and 32 width. And the data type is float32. So we're converting the data type of the first batch from torch.float32 to float32. But convolutions in JAX is a bit different than PyTorch. It gives you the flexibility of swapping the dimensions. So you have to be careful before performing these convolutions. So I got an example here. Suppose we have a batch of 2 images, only 2 images. And the size of each image is 32 by 32 by 3. 32 height, 32 width, and 3 channels, RGB. We're passing 4 filters of 5 by 5. And we're passing these across the image. How to order the dimensions for JAX.flax.conv general dilated. So here are the 2 images in the batch. And here are the 4 filters. JAX takes these parameters. I strongly recommend reading this tutorial because that's where I'm getting these parameters from. This tutorial, generalized convolution, is in JAX. Down here they have a description of the parameters that goes into these parameters. I got the same thing in the notebook. So N is the batch dimension, H spatial height, W spatial width, C channel dimension, I kernel input channel dimension, and O kernel output channel dimension. Here in the tutorial they say that these helper functions assume LCHW images and OIHW kernels. So the n-dimensional array for the input n-dimensional array should be arranged as follows. The batch size is the first, then the channel dimension, then the height and width. The filters should have these dimensions: the output channel, the input channel, and the height and the width. So if we look into our example with the 32 by 32 by 3 images and 2 images in the batch with 4 filters, the input should be two images in the batch, 3 channels, 32 height, 32 width. The filters are 4 filters in the output, and 3 channels they are getting as the input, and the height is 28, the positions that we can place the filter, and the width is 28. And the output has 2 images in the batch, 4 channels, 4 filters, and 28 height and 28 width. The flexibility of JAX comes from this function, flax.conv dimension numbers. So you tell basically what this function is doing. You give it your input and the filters, and you're passing what's the order. So if your dimensions are messed up, you have the batch dimension as the last dimension, and you have the height and width messed up. You pass your images and filters and tell this function what are your dimensions. Here we're telling this function that our input has the batch as the first dimension, the channel as the second dimension, the height and width. And for the filter, we have the output channel, the input channel, the height and width. And the output, we wanted the batch, the channel, the height and width. So basically we are passing the right thing to this function. That's why it didn't change any dimensions. So its output is 0, 1, 2, 3 for the left hand side, which is the batch of images, 0, 1, 2, 3 for the right hand side, which is the filters, and the output is 0, 1, 2, 3. But if your dimensions are messed up, you can use this function. So it's pretty convenient to use it in JAX convolution here at the end. So we're passing the batch of images, we're passing the kernel, and Windows tried, we're setting it to 1 by 1, and we're setting the padding mode to valid. Don't do any padding, and image dilation, not using image dilation, and we're not using kernel dilation. And the dimension numbers, we are passing the same variable that we computed using conv dimension numbers. So this function conv general dilated will compute the convolution, and its output shape is 32 images, 4 filters, 28 height, and 28 width. And the data type is float32. Here we're comparing the convolution output from torch with the output we're getting from JAX convolution function. Basically here we're subtracting both arrays, and we're taking the absolute value of differences, and we're getting the maximum difference. So the maximum difference is very, very small, indicating that these two arrays are similar. But if you run array equivalent, they won't be equivalent. I think there is some precision error, but let's plot the images from both convolutions and see how do we compare that. And I'm plotting the torch convolution, the first image, the first filter, all pixels in the height and all pixels in the width, and I'm detaching that and converting it to NumPy. This will go into the first axis, and I'm getting the output from JAX, first image, first filter, all pixels in the height and all pixels in the width, and I'm plotting that at the second axis. So this is how the first image looks like. These look similar, so we're getting the same output from JAX and from PyTorch using the same set of images. But be careful. Sometimes you test one thing and you get it right, but everything else is messed up. So we have to make sure. So I did plot all the first 5 images, and they look the same. So in comparisons, don't just compare one example, compare more than one example, just to make sure that you are getting the results right. So this is the PyTorch convolutional output, and this is the JAX convolutional output, and they look the same. One thing to note about these convolutions, if you are trying to compare with the output of flax.linen.conv or the output of torch.nn.conv2d, make sure that the weights of these two layers are the filters. But if you are pulling out the weights, make sure you pull out the biases as well. Because if you are comparing with these two functions, the conv general dilated or the functional.conv.2d, these two functions don't have bias. I got trapped in this myself. I was comparing the same thing between flax and JAX, and I'm getting way off. But when I get back to that, I was missing the bias. I was pulling out the weights, but I was leaving the bias. Make sure if you're comparing that, you pull out the weights, you add the bias, and you compare it with the output. My final remarks on this, I found that JAX convolutions are very flexible, but a bit hard to understand, especially the concept of dimensions. At first, it looks confusing, but then I start liking it. I'm not aware of anything in PyTorch that do that. If there is a similar function in PyTorch, please let me know. But this is very flexible, and I really like it because you don't have to do the swapping yourself. You don't have to do transposing. So I found this very neat and a very detailed implementation. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. By the way, you can find a link to the notebook I'm working on in the description below. Thanks for watching. Bye.